Right, so thank you for the kind introduction, and yeah, thank you for inviting me here. So this is my second time in Cardiff. The first time was in 1999, and I recognize the arcades and nothing else. So that has not changed. All right, so just to, I mean, I'm not sure in terms of time if I need to stop a bit earlier, because I think we're overrunning. That's fine. Like I can, yeah, or I can keep talking.
I will tell you 10 minutes before the end.
Okay. Yeah. So here is sort of at a high level the task that I care about. I've got two sets of objects, like two sets, and I want to know if these sets are from the same distribution or from different distributions. So I'm not even assuming exchangeability. It's literally independent, identically distributed samples. Okay. So this is, this is the theme of the talk. Immediately I'm going to jump into like a fun instance of where this challenge can be really difficult. So here I have two sets of handwritten digits, and on the left I have computer digits from MNIST, which is like the successor from USPS from Alex's talk. And here I have samples from a generative model. Now, the authors of the paper that did this, which was not me, claimed that humans couldn't distinguish the digits from a computer and the digits from a human. Like they were given these two grids in an Amazon Mechanical Turk experiment, and you were shown one or the other at random, and humans were performing at chance level. And yet, the distribution of the digits that a computer generates is in fact different, but the difference is subtle. So if you have like a very sensitive test of the difference in distributions, maybe you can find it. So a human can't find it, but the statistical tests that I will talk about, they will actually reject the null. They will basically conclude that these are from different distributions. It's a tough problem, but it is a possible problem to solve. It's high-dimensional, everything.
Can you simply explain why? I want to why now. Why is that different?
You will see. I'm going to show you actually. It's very subtle. Because this is a very good model, but it's not good enough. So we can break it. So yeah, so this is a nice question, but maybe this is a question that statisticians like to answer. The question that machine learners want to answer is, how do you get rich? And so here is the answer. If you have a good difference between sets of objects, you can use this also to train a generative model, to create samples that have the same distribution as your target set. So recently you might have read in the newspapers that somebody ran a generative adversarial network to generate a picture, a blurry picture of an individual, and then went to Christie's in London and sold it for $432,000. There's a fun detail of this. It was signed by the algorithm that generated it. Now, the people who run the algorithm actually didn't understand it, and they made a bug in the equation. The person who did run the algorithm, there's actually an internet, message board, where he was answering the questions of the people who sold this thing. So the guy who wrote the software wasn't the guy who made the money. Sad story.
But did they put this as an original, or they knew that?
Yeah, so they sold it as like the first computer portrait. Of course.
So people buy and use it. It's
yeah, and so they knew it was an artificial thing, and like the people who ran the code, who were not the people who wrote the code, just ran it, hit print, put it in a frame, sold it.
And they generate a lot of them, and after they select one that looks.
So they generated a few. I mean, but this is actually it's not terribly good software. So in the talk that I'm going to show you today, the pictures I'll show you are worth at least $1 million. So yeah.
Did they just normal HP printer, or they use some oil?
Well, maybe they used a fancy.
No, it's ink printer.
Oh, just ink,
yeah. So you can go down to your local printer.
Why some idiot pay for this one?
Yeah, there are people that have too much money. Yeah. This is not secret.
So, but by the end of this talk, you'll be able to do this yourself. So
I can go back.
You can be an
okay. So here is actually using a not so advanced version of our software, less advanced than the pictures I'll show you later. Pictures of bedrooms done by one of our networks versus pictures of bedrooms that are real. And actually, the features that you see in the fake bedrooms are not too bad. There is sort of some physical implausibilities among them, but the kinds of shapes you see, the kinds of colors, etc., these are more or less correct. And this was done actually with, a thing that was basically optimizing a statistic which compares these two sets. So I've got a statistic saying how far apart are these two distributions. I then minimize that over my training, my thing that's generating these pictures, until I can't minimize it anymore, until my sort of equilibrium has been reached. Okay, so this will be the second half of my talk. I'm going to talk about like how do you use this measure of distance between sets to train a generative model to generate nice features. Okay, so that's part 2. Okay, so part 1 will be a sort of more statistical part. Part 2 is going to be more machine learning part. There's a couple of things that I won't talk about today, but I wanted to just signal. So one, I've talked about finding the difference between two sets. What if you have a set and a model? So here I've got a data set. These are the crimes that occur in Chicago, and I've got a model, and the model is not very good. It's a mixture of two Gaussians, all right? So, what you notice about this set of red points is that there's a very sharp edge to the right-hand side. So the sharp edge occurs because that's where Lake Chicago starts. In Chicago, there are no pirates, and so no crimes in the water. Okay, and so our model is poor, but we want an automated way to say where it is that the model doesn't fit our data. So all models are wrong, of course, but what's interesting is to know why your model is wrong. This is something else we can do. Another thing we can do, which I won't talk about today, is to look for statistical dependence. So in this case, you've sort of got two views of the same object. So you've got a picture of a dog, and you've got a description which isn't a description literally of the picture. It's not, it's brown, it has 4 legs, it has a tail, but it's something that if you were an expert on dogs, you would understand probably referred to the same animal. Okay. Now what I want to do is to find dependence between the left and right columns. So knowing nothing about dogs, not knowing how to regress from caption to image, I still want to know if captions and image are dependent. So this is something else that we can do with a slightly more, a modification of the tools that I'll talk about. And again, I'm bringing this up so that people are alert to the fact that we have this. Yeah. All right, so here is the structure. First of all, I'm going to describe my statistic. It's called the maximum mean discrepancy. There's an easy way and a slightly less easy way to understand it. The easy way is just as a difference in feature means. I've got my feature mean of P, my feature mean of Q, and I look if they're different. Okay. Slightly more complicated way is as an integral probability metric. I'm going to talk about exactly what that means when I get to it. So that's something that ends up being the more useful view when it comes to training generative adversarial networks. So that's why I'm going to use it, even though it's slightly less intuitive at first than this difference in feature means. And then I'm going to talk about how to use a statistic to train my generative adversarial networks. Turns out you can't just plug it in, you need to actually make some modifications, which I will explain. Alright, so maximum mean discrepancy. Let's start with a simple notion to describe it, which is the difference in feature means. So, very simply, statistics 101, if I had two Gaussians, I would actually, and they had different means, I would just compute the difference in expectation. If it's large enough that it's unlikely to be due to chance, then I would reject the null. But what if I have two Gaussians with the same mean, right? But they're not the same Gaussian. So here the intuition is that I look for the difference in expectation of a feature. The feature is an obvious feature here, it's x squared. The chi-squared, your distributions of these features are chi-squared. The means, of course, are now different. So I could make a statistical test based on these features, expected features. All right. So now what happens if I have two distributions and they have the same mean and they have the same variance? Well, in this case, if I use the feature from my previous slide, I would be in trouble. So I might then say, well, I'll just think of another feature. I'll use x to the 4th. But then, of course, I'll find two distributions which agree in expectation for that feature, and then I'll need another feature. So, I could continue the discussion, but ultimately what I want is an infinite dictionary of features so that I can never be tricked. Okay? So how do we construct and deal with infinite dictionaries of features? Well, one natural way to do it is to use reproducing Kernel-Hilbert spaces, because they give you infinite feature dictionaries built in. Right? So, just to introduce the notation, I'm not going to go into much detail about the theory of reproducing Kernel-Hilbert spaces. I think some of you probably know that extremely well already. But my point x, this might be my picture of a dog or whatever, I define a vector of features of that object. All right. Now this vector of features is could be countably infinitely long. It's square summable though, so I require that the sum of the squared values of my features of my point has to be finite, even if there's infinitely many of them. And my kernel is just my dot product of my features. Okay. So the trick when you're using kernel methods is that as long as my algorithm only uses dot products, then I can use an infinite dictionary of features. Because, I never have to write down the infinite dictionary of features, I just have to write their dot product. All right. Here's a nice example of a kernel, which is a dot product of infinitely many features. It's the Gaussian kernel, exponentiated quadratic kernel. And so what you can see about these features is that as you sort of increase your dictionary index, the features get more and more wiggly. These are Hermite polynomials with the Gaussian decaying envelope. And the amplitude of these features decreases. All right, so wiggly features have smaller amplitude. These are not a unique dictionary of features. There are other features that give you the same dot product, but these are one representative dictionary that I could use. All right. So I've talked about not features but expected features, and it turns out that you can use the same sort of trick for expected features as you can use for features. All right. So here is my dictionary of expected features of a distribution P. So I just take the expectation of each of my features, and for positive definite kernels, the dot product of my expected features is my expected kernel. Okay. So I'm allowed to take my expectation outside the dot product. This is a little bit of a tricky thing to verify. What you need to check is the expected norm of your features, so the expected length, so to speak, of your features is bounded. If it's not bounded, you can't just take an expectation inside and outside the dot product, because you might end up getting an infinity, which you might not like. Okay? So as long as in expectation your feature norm is finite, I'm allowed to take my expectation inside or outside my dot product, and I'm getting that the dot product of expected features is the expectation of my kernel. This is very good news in an algorithm, because as long as my algorithm only uses dot products between expected features, then I only have to deal with my kernels. Okay, so what's a very simple algorithm that only uses dot products between expected features? Well, I would just take the norm of the difference of my expected feature means. Because when I expand that out, then I end up getting, dot product of expected features of P with itself, expected features of Q with itself, and then expected features of P and Q. Using the result from the previous slide, I just get a sum of 3 expectations of kernels. So something which is very simple to compute. All right. So let's see what this looks like when I do it based on samples. Okay. Here are my dogs and my fish. Each of these values, each of these squares is the kernel between one and another object. So if you think of a kernel as a dot product, if the 2 feature vectors align well, the dot product is large and the objects are similar. If the 2 feature vectors are close to orthogonal, the dot product is small and the objects are different. So you can see that a dog is very similar to another dog, but a dog is not so similar to a fish. Okay? What is my statistic? Well, my statistic is the average dog-to-dog similarity plus average fish-to-fish minus average dog-to-fish. So obviously, because dogs are more similar to dogs than they are to fish, these 2 first terms are going to be large, the third term is going to be small, and my statistic will be large. Okay? Whereas, if I had dogs all the way, then on average the diagonal blocks would be equal, up to noise to the non-diagonal blocks. I would get a small number, and I would conclude that it's unlikely that my dogs and my fish are from different distributions. Okay. So, this also illustrates that, I'm finding a difference between the expected features. I have infinitely many features, but the computation that I've done has never required me to write down that dictionary of infinite features. I've only had to write down the dot product of the features. Okay, if there are any questions at any time, by the way, ask me. But this is pretty simple. Okay, so this is my statistic, and this is one way to look at it. I'm now going to describe another way to arrive at the same statistic, which initially is going to look like it's a different approach, but then I'm going to show actually it's the same approach. All right? So if I show you these blue and red points and I ask you, are these from different distributions, then you're probably going to say, well, yes. Okay? Now what about if I show you these two sets of points? Well, you know, who knows? Maybe if you show me more points from the same distribution, there will be a difference. Maybe not. You know, but on the strength of the evidence here, it seems that these are further apart, right? Yeah. Okay. So how do I formalize this intuition? What I could do is I could say, well, give me like a well-behaved function, like a smooth function that maximizes the difference in expectation. All right? So in this case here, you can see that my smooth function is very positive on my blue points, very negative on my red points. When I take this difference in expectations, I get a large number. But the function has to be smooth. So now if I do the same thing here, I look for a smooth function that maximizes the difference in expectation. Well, the smoothness means that I cannot make my function very positive on my blue points and very negative on my red points because it's smooth. It's not allowed to change much from point to point. Okay?
What do I mean smoothness?
I will tell you shortly. So I've been very vague about that, deliberately vague, maybe. So yeah, what is my class of well-behaved functions? Well, what I can do is I can say, well, let's use a unit ball in a reproducing kernel Hilbert space. Let me use this as my class of smooth functions. What does that mean? What that means is that I take as my function a sum of the features that I defined earlier. Okay? Where when I say unit ball, what I mean is that the sum of the squared coefficients of these features is less than or equal to 1. Okay? So f1 squared plus f2 squared is less than or equal to 1. You know, what that means is that my function is smooth because I'm taking a sum of coefficients whose sum is less than or equal to 1, each of which multiplies a feature. These features get less and less smooth as I go up. The amplitude drops. The amplitude of my f also drops. It has to drop because the sum of the squares less than 1. So I end up getting a smooth function out. So this is my smooth function. All right? I'm faced again with a slight dilemma, which is that I can write it down like this, but I can't compute it because I've got infinitely many features and infinitely many coefficients, so we'll return to that problem later. But for now, this is my smooth function. Okay. Here is my Gauss versus Laplace example from before, and you can see that this approach solves that problem because I can define a smooth function which has a large amplitude where the probability mass of P and Q is different. Okay, because I've got more points from the blue here, I've got a large amplitude, then I've got more points from red here, I have a large amplitude in the opposite direction. That's going to pull apart my expectations, and I'm going to get a large number. So that's going to work. Okay. So, the trick that I showed before about taking expectations inside the dot product, I can do it not only for features, but also for functions. So if I've got my expectation of my function of x, that's the sum of the coefficients, defining my f, f1, f2, f3, and my expected features of x. So again, subject to the constraint of the expectation of the norm of my features has to be bounded, of course, otherwise this is not allowed. I can take my expectation inside my dot product. Alright. So, I've talked about using functions in a smooth RHS. Under what circumstances am I guaranteed that this statistic is 0 only when P and Q agree? Okay. So there are certain kernels for which this is true. It's sort of saying I've got infinitely many features, and that feature dictionary is rich enough that this quantity here is a metric on probabilities. It's 0 only when the probabilities agree. Yeah?
Why not just use cross entropy?
Cross entropy. So
Use a screw back distance. So what's better?
It's more easy to compute with
Yeah.
kernel.
This is very simple to compute. So KL, we've like you can do tests with KL. I can do tests with KL. A challenge with KL is that like estimates of it are very troublesome, particularly in high dimensions. For estimation,
It's numerical because
Yeah.
it's 0 if and
Yeah.
only if it's coincide.
Yeah, yeah.
This is far more flexible and easy to compute.
Okay.
Yeah.
But there is no triangle inequality, nothing like that for and it's not symmetric.
yeah.
Okay.
But for testing, though,
we are not talking about triangle
Yeah.
equality here.
Sometimes we do.
No,
Here with this you have all the geometry you want. This
Yeah,
is good.
you're in a Hilbert
Okay.
space.
No,
Hilbert
I'm not
space is
trying.
nice.
I just, there's no question. Why not? Yes.
No, it's a probometric inequality. No, there is triangle.
Yeah, you're in a Hilbert space, so you have every
Okay.
property of a Hilbert space you
It's a
have.
probometric.
Yeah.
Because there is triangle. But not for yours.
Yeah, not
Yours is
okay.
dodgy.
Unfortunately, it's not mine. It's not mine. I wish.
You wish.
Mine, yeah.
Yeah. So Yeah, I mean, so for a rich enough dictionary, this is a metric. And I will talk actually about the link with KL later. That's something that's coming up. So how do I check this property? I'm not going to do the proof because I've got limited time, but I can tell you a little bit the idea. Basically, a way to quickly check if your RHS has that property, if your kernel is translation invariant, take the Fourier transform. If it's 0 on an interval, it's not characteristic. If it's 0, like only at points, or not 0, then it's characteristic. So, yeah, I can talk about why that is, but like that's just a quick way to check. Yeah.
It's only for when the symmetric. When
Yeah, translation invariant.
T minus S, yes.
Yeah,
Rotation
absolutely,
invariant.
because you need buckness there.
You want that to be universal.
Yeah. So universality means that you're dense in the space of bounded continuous functions. So that's actually a property for compact domains, which implies that it's characteristic. But when you're on non-compact domains, universality, there's different definitions of universality, like C0 universality. And they're not, characteristic and universality, the relation is more complicated on non-compact domains. On compact domains, it's equivalent. Yeah, there's a review paper by Bharat Sukarambudur, Kenji Fukumitsu, and Gretton-The in 2011, which does the non-compact case as well, and like that's the relation. But universality is a property of the richness of the RHS in approximating continuous functions. Characteristic, I use that term only to mean that the embedding of a probability measure is injective, and so. Sometimes these are the same thing, sometimes not. Yeah. But this class of metrics, I can use other measures. I can use, if I want to get the Kolmogorov metric, I use functions of variation 1. If I want to get the Wasserstein class, I can use bounded Lifshitz. And I mean, all of these are instances of this framework. Yeah, and these collectively are called integral probability metrics. All right. So I want to show now in just one slide that looking for differences of expected features is equivalent to looking for smooth functions that maximize differences in expectations. And here we use a very pleasant property of Hilbert spaces that they're self-dual. You're going to see shortly how this works. Okay. So let's start. First of all, we have here. I show you with my mouse that here is my definition of my maximum discrepancy, the maximum of functions in a unit ball that maximizes difference in expectations. All right? Next slide. I remember that the expectation of my function is the dot product of the coefficients that define it and the expected features. Okay, I'm allowed to take my expectation outside of my dot product. Okay, so then I have the dot product of the f, my coefficients, and the difference of expected features. All right? Now, what is the f in a unit ball that maximizes its dot product? Well, I'll give you the graphical clue. Here is my f in my unit ball. Here is the vector that I'm trying to maximize the dot product. And we can guess what it is. It's just the unit vector in that direction. Okay? So when I take the dot product with the unit vector in that direction, I just get the norm of the difference of expected features, and I've shown the equivalence. So this is a very nice property because I'm in Hilbert spaces that normal difference of expected features is the same as the integral probability metric. So this is nice. Function view and feature view are
Square.
so I didn't square it. I'm just looking.
No, it's square root already.
Yeah.
Because
exactly.
norms.
Yeah. So. So how do I get my witness function? This nice function that I plotted. I'll show you first the construction algorithmically. Yeah.
Witness function which is supreme.
Yeah, exactly. So this f function here. Yeah, I'll show you the computer from samples. So here are my observations, x and y. If I use, for instance, this Gaussian kernel, I put Gaussian kernels on all my blue points, Gaussian kernels on all my red points. I add the blue functions together, I add the red functions together, I subtract red from blue. That is my function up to scaling. Okay? Now, why is this true? Let's find out. Remember that my f, my witness function, is up to scaling the difference of expected feature means. Okay? Now, if I've observed samples, well, what is my feature mean? Well, it's just the empirical average of the features of the points that I've observed, right? So here's the empirical average of the features of the points. now, what is the value of my function at a point v in this case? Well, it's the dot product of the coefficients with v, with the feature of v, right? Because that's true for any function in our case. Okay, what are my coefficients? Well, up to normalization, it's the difference of expected feature means, dot producted with the features of v. And remember that the dot product of features is a kernel, so now I've just got the kernels between each of my samples and my v minus the kernels of each of my y samples and my v. So this is showing that in my kernel space, my witness function is just the differences of the kernels on my blue points with the kernels on my red points. I don't have to write down the coefficients to get my witness function. So as I promised, here is my witness function with no coefficients explicitly defined. All right.
So how do you define this function?
So I have samples, right? So this is a sample one. Now, of course, as I see more samples, I can show that in our case,
that function.
yeah.
Well, just no, okay.
Yeah. So I can define, the normal of this is easy to compute again in terms of.
Can you write something in the language of machine learning?
It is machine learning.
This is machine learning.
Yeah, I understand, but somehow, what is the loss function? It's a minimizer, it should be loss function.
Yeah, or
Okay.
in this case, it's a maximizer, right? It's the thing that
Okay.
maximizes the difference in means under P and Q. Yeah. Subject to the smoothness constraint, the unit norm constraint. Yeah. So it's nice. It's kind of nice because it's a function which it tells you where it is that P and Q are different. So this large positive amplitude on the blue and large negative amplitude on the red. So it's sort of telling you here there are more blue points, it's positive. Here there are more red points, it's negative.
You just put problem machine learning function from sample
Yep.
with such loss,
Yes.
and I run canonical this kernel algorithm, this will be.
Yeah, I think so.
Yeah, exactly. So the loss is a linear loss.
I have to keep something in my mind.
You want to translate all the time.
Yeah, I translate something.
So you're very slow then, yes. So every time you need to translate.
So my loss function is a linear loss. My regularizer is this, smoothness, and this is the function that satisfies. Yeah. Okay. Cool. So this is my relation with KL. That's your question. So, broadly speaking, if I want to tell apart two distributions P and Q, I have two ways to think about it. I can think of it as a difference, or I can think of it as a ratio. Like this is, very qualitative. I'm not making anything precise yet. Okay. So if my difference is 0, P and Q are the same. If my ratio is 1, P and Q are the same. Like, very broadly speaking. Okay. So these two sort of philosophies of divergence give rise to two different families of measures of distance, right? So the integral probability metrics, these are built around this notion of difference of probabilities. So I'm looking for a function in some class, which I've written here H. It doesn't work. Okay, H. That maximizes my difference in my expectations, right? So the notion of difference occurs. Okay? Or on the right hand, I'm finding something that tells me, about my ratio. In this case, I'm finding the expectation of a function of that ratio. Now, obviously, if my ratio is 1, I want my f to be 0, right? And my f is going to be convex as well, and then I'm going to get, a nice class of distributions. So among these, I've got Wasserstein and MMD. Among these, I've got Hellinger, I've got KL, I've got chi-squared, all of those families. And you notice that there's an intersection, and that intersection is not empty. So only one non-trivial divergence measure lives there. Does anyone want to guess?
It has to be log somehow, yes.
Total variation. So the L1 distance is the only one that is both. Yeah.
So it's just sort of variation.
So so
What is
integral. So you can think of like integral of p minus q. Okay, absolute value, and then I can say, well, that's the integral of p on q minus 1, absolute value, dq. Shall I write it?
You need infinity norm or something.
Hang on, it's the L1 distance. Do you have a pen here that is for the whiteboard? I can't see what.
Yeah.
No.
Nope.
Wow.
Well done.
Oh, that's really infinite. Right, so I've got this, p minus q, absolute value dx. And all that I'm doing is, it's just a simple thing, right? P on q minus 1 Qx dx, right? And so then my f of P on Q is just the absolute value of P on Q minus 1. This is my f. So that's it. I mean, it's not,
Okay, something to multiply by Q is the same function.
yeah,
Okay.
so exactly. So I want to, integral of Q of blah, blah, blah. Okay, so this is my f. Yeah. So that's that. Yeah.
Well, I call this total variation. Sorry, for me, total variation
I
is
mean,
the integral of the grad function.
Yeah, this was not my name.
Okay.
But, yeah,
It's the absolute value or something.
yeah.
So it's not total variation from image
No,
processing.
no,
Okay.
that's
Yeah.
confused.
I will use, the reason I called it that is because it fits in this little
Okay,
thing.
perfect.
Yeah. Actually, I could have written L1, that would also fit. Anyway, yeah. Okay, so my next thing is, like, I have a statistic I want to do, for example, a hypothesis test. So it's going to be an asymptotic hypothesis test, but fortunately, like, Alex isn't here to, like, yell at me for doing this, so, so here is my statistic. Which, average P to P sample, average P to Q minus average P to Q, okay? So I need, in some sense, a threshold which determines when this distance is sufficiently far from 0 that it's unlikely that P and Q are the same in some respect. All right. So let's see, I'm going to require a false positive rate alpha and a threshold such that when P and Q are the same, I will exceed this threshold with false, false positivity rate of alpha. Okay. So let's look at how this statistic behaves in the event that P and Q are different, first of all. Okay. So here I have a sample from P and Q, evidently from this sample, they're not the same. The red has a bit higher variance than the blue. Okay, this is a scatter plot. And my statistic, multiplied by root n in this plot, is 1.2. It's a number. Okay, that's how far apart they are. Okay, so here on the x-axis, I'm going to put the value of my statistic. On the y-axis, I'm going to say the probability that I saw it. Right now, I've just generated 1, so I see just one value with probability 1.2. Let's do the experiment a second time. This time I see 1.5, so I put a bar at 1.5. Let's continue 150 times, 300 times. I had a really long flight, so 3,000 times. And you can see that this was, starting to look like a Gaussian, and indeed that's what it is. Okay, so basically my maximum mean discrepancy is asymptotically normal when P and Q are different. Okay, for those of you who've encountered U statistics before, this shouldn't surprise you because the MMD is a difference of two U statistics and a sample mean. So a U statistic, in the non-degenerate case has asymptotically normal distribution. This is something constructed with U statistics, it's going to be asymptotically normal. Okay? And so you can see, in fact, it's a pretty good approximation.
Can you compute the variance?
You can. There's a closed form expression for the variance, yeah. It's actually quite simple. You can do it in the same time if you do it in a clever way, I guess. You can compute it in the same amount of time as the MMD, which is to say quadratic in the number of samples. It takes a little bit of work to do it that way, but you can, yeah. But we have expressions for the variance. Okay, so this is our statistic, but it doesn't quite, this asymptotic normality doesn't answer our question, because our question was, when P and Q are the same, how do we make a threshold such that we exceed that threshold with some probability? And I haven't answered that question, because here I've shown you what happens when P and Q are different. Okay, so let's see what happens when P and Q are the same. Okay, P and Q are the same. I've generated 10 values of the statistic. Here I've got n times MMD on the axis, so that already should worry you a little bit. And probability of seeing it. So one thing you'll notice is that when P and Q are the same, I'm seeing some values of my distance between P and Q which are negative.
But it's squared, how can it be negative?
Exactly. So, but it's an empirical estimate of a quantity whose mean is 0. So, it's an unbiased estimate. I'm going to see some stuff negative, I'm going to see some stuff positive. And you can see, even empirically, why that should make sense, right? Because I've got empirical mean of P to P plus mean of Q to Q minus mean of P to Q. If P and Q are the same distribution, then just by chance,
You
occasionally-
put hat, no, it's
Yeah.
just by notation, because you should put white hat, because
Oh yeah, over the
I
square.
think, yeah, because
Yeah.
first impression you put,
Yeah.
compute something and take square.
Yeah. No, so actually you're right. Yeah, the notation, the better
Yeah,
notation would
okay.
be hat
should
over
be-
the square.
Yeah, hat should be over.
Yeah. So think of this.
All right,
this
okay.
hat over the square. Okay. So here is 20. Okay. Here is 50. Here is 100. Here is 1,000. It's not looking very Gaussian. Okay. Why is this? Well, in this case, when P and Q are the same, we have degeneracy. So it's like a degenerative statistic. And the asymptotic distribution of the statistic in the event that P and Q are the same is very, very different from Gaussian. It's an infinite weighted sum of chi-squareds, where the weights of the solution of this eigenvalue problem here, where the eigenvalue problem is a function of the P, which you don't know, and the kernel, which is being centered in feature space. And the centering you can't do either, because it has to be centered with respect to P, which you also, you continue not to know. So basically, like, I want, for my test, a quantile of this distribution. But this distribution, well, is an infinite weighted sum, and I can't compute the weights. So that seems annoying. Okay? So what do I do? So here is a summary of the asymptotics. When P and Q are the same, I have this rather strange looking distribution. When P and Q are different, I have this normal distribution. Like this is how I expect my statistic to behave in these two scenarios. Okay? This line that I've drawn here is the line that I want to get. This is the probability. This is the threshold, the 1 minus alpha quantile of my red distribution. So when P and Q are the same, the probability of exceeding this threshold is going to be alpha. It's going to be something small. What is this blue area? Well, this is my probability of false negatives, and I'm going to return to that later. But this is, if P and Q were different, that area represents the probability that I make the mistake that I think they're the same. Okay. So, here is my statistic, average P to P, average Q to Q minus average P to Q. I've got my dogs, I've got my fish. How do I use this to simulate from the case where P and Q are the same? Okay. So here is what I can do. I can shuffle my data, right? So I can take all my data, put it in a bag, throw half of the bag, call it P, half of the bag, call it Q. So I'm doing the shuffling without replacement. So here we're getting like merdogs, which is sort of half fish and half dogs. Okay? Now what is the matrix of kernels for merdogs? Well, actually, this looks pretty uniform, which is what you expect, right? So on average, the similarity between x tilde and x tilde is the same as the similarity between x tilde and y tilde, because each of them is sort of like a 50-50 mix of dogs and fish. Okay? So this is a way to simulate from the case that P and Q are the same. And it's slightly tricky to prove, but you can prove that the quantile you get from the shuffling, when P and Q really are the same, you will get the right quantile. It's not easy to prove, but it's provable. When P and Q are different, you're going to get just a fixed quantile. It's going to be a quantile sort of simulating this mixture case. And any fixed quantile will give you a consistent test in that your type 2 error is going to go to 0 as you see more samples for any fixed threshold. So you have a consistent test, and you have a test that gives you the right threshold under the null. Okay, so the shuffling approach is an approach to get around this problem. Okay. So the next question you might ask is, like, how do you choose the best kernel? So, I've got any number of kernels I could choose. I have a task, a testing task. How do I choose the best one? All right, let's find out. So what do I mean by the best kernel, actually? Because that is a worthwhile question to ask. What I mean by the best kernel is, for a given false positive rate, I want to minimize the number of false negatives, right? Because if I succeed in doing that, then I will have a good test. Right? Of all the kernels I choose, false positive rate is fixed. I decide on it. But what I want to do to choose a good kernel is to minimize the number of false negatives for a given false positive rate.
But then it will depend on your alternative.
It will depend on the alternative. That's correct. Yes. So the best kernel is a problem-specific answer. Yeah. Okay. So here is the probability under the alternative of rejecting the null. Okay. So probability under the assumption that P is different to Q, that my statistic is going to be bigger than my threshold. Now remember, under the alternative, I was normal. All right? So this has a very simple expression under the alternative. I don't have to worry about my infinite weighted sum of chi-squares. I've got this standard CDF of my statistic on the variance under the alternative minus this threshold and divided by the same variance. Okay. So I want to then choose a kernel that maximizes this amount, right? That I want to maximize the probability that I reject the null. All right. So what do I have to play with here? I've got this MMD, that's a function of my kernel. I've got my variance, that's a function of my kernel. I've got this C alpha, that's a very, very nasty function of my kernel, because it's that infinite weighted sum of chi-squares where the weights are a function of my kernel. Okay? So it seems that to choose the kernel to maximize this might be very troublesome. And the reason for this trouble is the C alpha term, which is a function of my kernel in such a complicated way that I have really no way to figure it out. Okay? But fortunately, when I look at this variance term, I notice that my variance is going to decay as 1 on n, so that means that my standard deviation, square root of variance, is decaying as 1 on root n. That means 1 on the variance is growing as root n. This term here, I've got n times square root v, so that's basically n divided by square root of n, which is square root of n. So here, this term is decaying as 1 on square root of n. So basically, this term is growing, this term is decaying. So as long as n is large enough, this term, which has this annoying C alpha in it, kind of doesn't really matter.
How does it decay if it is numerator decaying?
So square root of v is decaying as 1 on root n. Okay, so n times 1 on root n is square root of n. Then 1 divided by square root of n is this.
Altogether, you mean?
Yeah. So this.
Again,
so
it's just the denominator is
I could
decaying.
put, imagine there's invisible parentheses.
All right, okay.
Yeah. So, yeah.
Okay, all right.
So basically, this term is growing, this term is decaying. So after not so many samples, the effect of this doesn't really matter. And this is true in practice as well. We've tried it. So ultimately, what matters when you're trying to maximize test power is to make your statistic as large as possible and to make its variance as small as possible, which isn't too unintuitive, right? And so this is the main thing that we do. Graphically this makes sense, right? I've got some fixed threshold, I want to push my mean out to the right and I want to make it very skinny. Then I'm done. I'm going to make this area small. Okay.
So but you do it for instance, Gaussian kernel and you play on the parameter.
Yeah. So here is actually an example. Here is this ms versus gan. And in this case, I can show you actually what my kernel looks like. If I've got like a kernel between two images, let's call this one x and x prime. It's going to be product over pixels in some set of pixels of a kernel between pixel p of image x minus pixel p of x prime. Well, norm squared, but it's just a value, so it's just the value squared, negative, divided by sigma p, okay? So sigma p is sort of like the length scale that corresponds to particular pixels. So an irrelevant pixel, I would just blow this up to something really huge, so that this thing would be very, invariant to the argument. But for pixels that are important in distinguishing one grid from another.
So it's also weighted exponent of weighted quadratic norm.
Right, exactly. So I've got just the square difference between my pixel values,
the weight is the norm, and this is the weight for each order.
Precisely. Yeah. And here,
how you calculate this?
Yeah. So I need to I learn these weights. So to maximize this ratio here.
But you learn for your data set. It's not something that you can tell me calculate like gradient or.
Yeah. So I learned it on the data set, but very importantly, it's not the data set I'm testing on. Because if I learn it on
I understand that, but you don't have explanation what it is. Like, for example, I don't know, Laplace of, Is this point or something like gradient, so sharp edge or whatever?
No, so in this case, like literally all we're doing is like looking for the pixels that are important in distinguishing the human and computer images. Yeah.
It's now the
But
question.
it's, yeah.
Suppose I blur this, with Gaussian blur this to set.
Yep.
What's happened?
Yeah. I think, yeah. I mean, I would maybe use a Laplace color rather than Gaussian. It could be, yeah.
Now if you blur, really blur this image, for
Yeah.
example,
Yeah.
5 by 5, can you distinguish?
I don't know, actually.
You know, blurred image, it's another question, yes.
Okay.
Because usually all these you said important pixels, they disappear with the blur.
Yeah, I think it would be, the problem would become harder, I think, yeah.
All simpler, they're just the same.
Yeah, but here you will not see, when you will estimate, you will find important region. You will
Yeah.
not find just,
Yeah, it
you
will
will
not be
find
able to-
cluster of,
Yeah, so blur
It'll be a
will-
neighborhood of pixels, yeah. Yeah, I think it will still be possible. It may be harder, though. Although, yeah, so if you look, like here are the plot of the important pixels. I mean, these are the ones that are switched on. And you can see a sort of bar down the middle, and you can see a sort of ring around the outside. So these are the pixels that matter when you maximize test power. I mean,
You know, it's very similar when you run just a random forest. Random
Okay.
forest on a mini-east,
okay,
and after that you select up to like 10% the most important feature pixel.
okay.
It will give you something like this picture.
Oh, well, this is cool.
I will
these
show,
are the
I will show you
pixels-
just
Okay.
we did this, you
Cool.
know.
Oh, that's cool. I mean, because these are the pixels that are also the ones that distinguish real and fake.
Yes, and they come
So
from
that's
when
very
you
cool.
run random forest, and after
Okay.
that just in scikit-learn just ask 10% of
Uh-huh.
most important.
Ah,
you
that's
have
super
picture
cool.
like this.
Okay, no, that's very interesting then. No, so then we have found the same pixels using like a quite different route.
Yeah, it will be cool. Yes.
This is very nice.
So,
Yeah.
so when you say optimize, are you saying about these coefficients sigma p?
Yeah.
So,
yeah.
but what about shape? What about this 2? Because I really don't like the 2.
So what we could do as well is to add to our dictionary, like we could take, something like, a weighted sum of these,
With different
and then another one with like a different exponent. So
With different exponent.
yeah. So we can add these.
I just
Yeah, and then you can you will learn the weight, and if it
and
turns out that this one with the single
1.5
one
or
is better,
whatever,
you're gonna win.
Try
That
one
one
of
will
these.
win.
Do I have slides?
What?
Do I have the slides?
Yeah, I can give the size. Yeah.
Yeah.
So if you remember also this like witness function, here I've plotted the digits which occur at the peak of the blue part in the witness function, so the most human-like digits. And these vertical ones are the most human-like digits. So what the subtle thing that this adversarial network is getting wrong is it's not generating enough vertical ones. Like it's failure mode. You can get some funny digits here, which is sort of like, you can see that it's adding sort of dim pixels in the wrong place, like a 5 that's almost a 6. And so these are a computer style error.
So sorry, I'm very slow. Can you come back to the problem of optimizing weights? What is the problem?
So
Is it
yes,
always
2 minutes delay.
It's
so sorry,
no, it's,
giraffe.
yeah, it's very non-convex.
Yeah, but how can you solve it? Because you have
Yeah.
so many weights. Each
Yeah.
pixel has a weight. If it is very non-convex, how do you do that?
We're not solving it optimally, we're initializing some median distance between these and then doing gradient descent. And then the pixels that are in
Yeah, but you just said it's very non-convex, so
Yeah.
gradient descent might be not very clever. I mean,
Yeah.
it could be very
So it's
non-clever.
true. No, it's true. So this answer may not be the optimal answer, but it's good enough for this task.
So there is no partial convexity, nothing.
Nope. No. We are very naive in our optimization. We do not do anything
You
clever.
divide or whatever. It's
This is
essentially
what I like.
Yeah. This is a machine learning solution to the problem. We don't try and solve it well. We just solve it well enough. Yeah.
This is what I like.
Okay, all right, sorry.
Yeah.
Because I thought, oh, you optimize.
Ah, no.
But I thought you
We,
cannot optimize because.
Yeah, it's very non-convex. So we just do it.
Okay.
We get more powerful
You
tests.
just do something,
Yeah.
okay, but towards that.
Yeah.
Okay,
So, but
fine.
for the problem of testing, it's sufficient. Yeah. I mean, in the sense that the power that we get is much higher than the power.
Yeah. I'm not
Yeah.
saying that.
Okay. So this is this. So let's see. How much do I have?
I don't know. How much do you need?
How much do you have?
When does my train leave? Is there
Yeah.
Okay.
But
Like, just
even
tell
by
me-
the timetable, you still have 15 minutes.
Oh, good. No, that's perfect then. Yeah. Okay. So now I've told you how to tell sets of samples apart. I've told you how to find if the difference is significant. But what I haven't said is how to use this to train an adversarial network. So now we're getting to the machine learning part of the talk, which is the next part. So I think a lot of you may have heard of adversarial networks before, but for those who haven't, I'm going to give a cartoon introduction. So there are three ingredients in an adversarial network. We have a generator, whose task is to generate samples. We have a critic, whose task is to criticize samples, and we have a task. In this case, the task is to draw pictures of dogs. Okay. So, given a student, given a critic, given a task, how does an adversarial network function? So first of all, the student generates some dogs, a set of dogs, and then the teacher compares the set of dogs that the student made to a set of real dogs, and then says, oh, that's not very good, and gives some feedback to the student to help the student improve. And then the student will generate another set of dogs, hopefully a little better. Critic will compare that set to a set of real dogs, give feedback, and the cycle will continue either until the student stops improving, or the teacher can no longer tell the real and fake dogs apart.
From pedagogical point of view, what kind of feedback?
So that is a question I will answer shortly. Yeah.
No, it's not violence.
It could be. Yeah. Depends on the student.
Yes, yes.
So, yeah. One important thing to emphasize here is that the task of the critic is not the task of classification, but the task of comparing sets. Like, it's important to look at it from the perspective of comparing sets. Now, here is why the task is not a task of classification. Like, if the task were a task of classification, then the student could answer that question by learning to draw one dog really well. And then the teacher would say, this is a dog, I'm sure it's a dog. And then the job would be over. But this is not the task we want the student to learn. We want the student to learn to draw all dogs and not just one dog. So that's the difference. Okay. So we have something that seems to be a good teacher, right? Which is the MMD. MMD compares sets. Maybe that's going to be enough, right? I've got my set of dogs. I've got my set of fake dogs. I use MMD. That's my teacher. I'm done. The challenge is that even on something as simple as handwritten digits, using an MMD directly on your data tends not to do very well, because the features that you use by designing a generic kernel may not be good features for telling images apart. Like, these are just these generic Hermite polynomials. Like, why would they be good image features? Probably they're not. In practice, you get this sort of like pixelated digits, which makes sense because the kernels that you're using don't have any sort of geometric meaning. Like, they're just like each pixel I could permute and it would be the same digit. And that's clearly not what's going on for real digit.
Can you, for example, map using some of the deep net to some almost...
Next slide. Yeah. So, it's like a telepathic, yeah. So here is what we actually do, right? We need to have a deep net which maps our images and like extracts reasonable features from our images to feed into our MMD. Once we've done that feature extraction, MMD is fine. Like generic features on good inputs is good. The challenge though is like, how do you actually choose good features, right? Now, one question might be, well, one solution might be, I will just choose the features that make my MMD big as possible. That's not a good answer, because then the features are going to learn some like very like narrow, specific, boring thing, like the bit rate of my image pixels or something stupid like that, and then it will give no useful signal to my student, right? So this is like learning features just to maximize MMD is not a good answer. It will quickly converge to something that is not helpful for the learning task. So we need to somehow learn these features, but also regularize the learning process in a way that is meaningful for the task we're trying to do. In other words, in a way that's meaningful in that it gives a good signal to my student. Okay? So here is one way to do that, which I'm going to later criticize heavily, but I'll start with it. Okay? These two papers, which were very, very influential, had a way to think about this problem, which is that if you remember this witness function, which has large positive amplitude on blue, large negative amplitude on red, right? These two papers say, well, if I force my gradient to be close on the points between red and close to 1 on the points between red and blue, then that means that I will give a good signal to my student. My student can then learn how to improve its samples towards my blue points. Okay, that seems reasonable. And so let's start with this and see where it gets us, okay? So here is my student. My student is a generator, so it takes a source of randomness, it puts it through some parametric mapping, in this case the parameters are theta, always theta for my student, and gives a sample y. So my parametric mapping is going to be a neural network, like reasonably complicated, so theta is very high dimensional, okay? My teacher, that is the thing that takes my images, puts it through some convolutional neural nets, and then puts something on top. Okay, maybe NMD, maybe not. Okay, so my features, my students of C, and my neural network that my teacher uses is H of C. Okay, so this now becomes a little bit notational, but it's actually quite simple. What these papers do is they say, well, I will take a linear function of my critic neural network parameters. I will maximize the difference in expectation of this linear function of my critic parameters. Okay. Plus, I will have another constraint. What does that constraint say? That constraint says that on points that are between my real and my fake images, I want my gradient to be close to 1 in norm. Okay. So this is like. So this is.
You want a clear cut,
Yeah.
No, but why is that norm should be 1? Why?
So their intuition, which I'm about to disagree with, is that if the norm of the gradient is close to 1 on points between the blue and red, that this allows my student to have like a strong signal to improve its samples.
Why?
But they have put 1, so certainly there is renormalization behind, you work on the stuff. What you want a clear cut, you want that it goes to positive to negative and it cuts.
Not necessarily. So, like for example, like let's say that here is my real samples and here is my fake samples. Then I could make this witness function. And this is not very helpful for my students.
This is not smooth. You say it in the beginning, you work on smooth stuff.
Right. So this is true. Now in this case, they have actually the only smoothness is like somehow implicit because it's created by the neural net. So in a sense, like this is their only smoothness regularizer. It's just a sort of Sobolev style regularizer. So that's also a point for their network. The only thing that is making their function smooth is this, because these are linear functions of the features.
Okay, that's so then.
Why not maximizing normal gradient or something? I don't know. Why is it 1? The normal
So
gradient.
so there is a reason they wanted it to be 1, which is that they wanted to somehow approximate a Wasserstein 1 critic, right? And for that one, like the gradient of the function is uniformly bounded by 1. But uniformly bounded by 1 on the domain is hard, so then they say, well, I'm just going to make it close to 1, not even bounded, but just close. On the
Usually such restriction appear when you try to iterate, because you have composition of Jacobian and you don't want them to blow up.
Right, right. So, I mean,
this will be
in
the
a
bad
sense,
solution at the end, so.
yeah. Well, there's about to be a problem. There's a couple of problems. But this is, this already made some progress. Like, this is not a disaster. We already tried something a little bit earlier, which is what we said, well, let's define the MMD on these features. So now my witness function is my kernel defined on my features of my data, kernel defined on features of data. And then, we have, in a sense, like two smoothness constraints going on. One is that we are requiring our f is in this unit ball, but we are also requiring that the gradient of our function, with respect to our inputs, is close to 1. So we just used exactly the gradient descent on the gradient constraint on our witness function just to see what would happen. And like it wasn't a disaster. It worked okay. So if you remember the bedrooms at the start, that was done by that software. So we did this in ICLR this year. The digits don't have as much pixelation. They're a bit better. Like these are actually not great samples. I've got better samples on that. But anyway, so why? Well, what is one reason why this is a bad idea? Okay, I'm saying that even though it's my paper. Here is a simple example showing failure mode of this way of regularizing. And it's a very simple example. Like there's no neural networks. Everything is just linear functions, okay? P is a delta function at the origin. So this is P. Okay, I want to learn to make a delta function at the origin. Q is a delta function at theta. My only parameter is a scalar. It tells me how far away my delta function is from the origin. I have a class of witness functions, which are linear functions of my input. All that it is the input times a scalar. Okay? So my generator has a single scalar it can play with. My witness has a single scalar it can play with. I want to use the scheme that I described earlier to train my generator to move its delta function here. Now, we can guess what's going to happen, right? I'm forcing the gradient of this function, this c here, to be close to 1 all the time. So here's the dynamics that you see when you run this. It's going to spin around, right? Because like it's going to run down here, but it can't slow down because this is being forced close to 1, so it's going to bounce this way and then bounce that way, bounce this way, bounce that way. It's never going to converge. So, you know, if my delta thing starts out here, I'm going to come towards the origin, but when I get close, I'm just going to oscillate.
Is that just average? Is it something balancing just like that?
Yeah, but I mean, averaging is a little
Okay,
tricky in high dimensions with the images. You're not going to get a nice picture. Yeah. So like the people who, like, you know, what we did and what others did was we just did a hack, like we dropped the learning rate, it stopped somewhere, where did it stop, we don't know. But, you know, you can stop it from bouncing, but it doesn't mean you get a good answer. Yeah. So actually, you know, what's a solution? So this is what we're presenting next month in Montreal at NIPS. We did a better gradient regularizer. So like, you know, what we were doing was something, I guess, inspired a little bit by the old supervised, semi-supervised learning literature, which is that, you know, what's a sort of data adaptive notion of smoothness? Well, it's that as we vary within our real images, our witness function shouldn't change too much. Okay, so like, you know, within the variability that we expect to see in the data, our witness function should remain flat. So it's a data adaptive notion of smoothness. And so this is all that we require. We say, like, you know, do the MMD, but perturb the witness function such that its gradient is small over the support of our real points. Okay? So this is what this looks like. Here is my like perturbed MMD. Here is my unit role, but my unit role now has this compound norm. Okay? So this is saying that in L2P, P being my distribution of my real points, my gradient of my witness should be small. Okay?
What does the semi-supervised regularizer?
So basically, you know, the semi-supervised learning was I guess in the sort of mid-2000s, there was a nice notion of semi-supervised learning. Like imagine I have like a set of points, you know, red and blue, but most of them have no labels. So then I have a decision function, and I want my decision function to be flat over the support, over the high-density regions. This is exactly the same thing we're doing here. We're doing it now on neural networks, but same idea. Yeah. Does that make sense?
No, they usually, no, because you know, it's a 2004, just beginning semi-supervised.
Yeah.
Usually what they have this time is just graph Laplace.
Yes, yeah.
And they use just VIJF,
Yep,
this
yep.
quadratic expression.
Exactly right.
And you use the same expression.
We do not use it because the graph Laplacian is an approximation to the smoothness constraint that we're using. So that was a graph-based one. We are not using the graph-based one. We are using like just...
Because 2004 was the very beginning of semi-supervised.
Yeah.
I couldn't expect something deep.
Yeah. So no, this, I mean, of course, like doing it with the graph Laplacian is not going to work in this setting, like way too expensive. So we are not doing it that way, but yeah. And we also add this because we wanted, like when lambda goes to 0, we want it to look a little bit like a soboletno. Like not exactly in ID, but like at least, you know, it gives more constraint. So does this work? Well, no, it doesn't. Why not? Trouble is we coded it up, and then it takes cubic time per iteration, and cubic time per iteration, like, you know, it took, I think, 4 weeks to train it to make digits. Like, that's just digits. Like, you're not going to make anything more. So it's like, it's a really beautiful idea, it doesn't work. Okay, what do we do? What we did is we just used like a simple Cauchy-Schwarz upper bound to get a scaled version of MMD, where the scaling depends on the gradients of our kernels and the value of the kernel. So it's sort of like, you know, rather than penalizing the gradient of the witness, we penalize the gradient of our features, we take the norm of the penalized gradient, that's our answer.
But what if your kernel is not differentiable?
Then you cannot do this. Yeah, we have to use differentiable kernels, yeah.
Because except for this square, most of the other kernels only once differentiable or,
Yeah.
or nothing.
I mean, if it's differentiable except for sets of measure zero, like if you
No,
go
no, it's on diagonal.
yeah, so that actually.
We're talking about diagonal now. No, diagonal they're usually not differentiable except for this one which has its own problems.
Yeah, yeah. I mean, so this one, it has problems, but those problems are very much mitigated by using deep networks underneath it. So, like, we use currently Gaussian kernels, and they work actually pretty well. We've tried also, like, other, so I think this inverse multi-quadrate kernel, I think, is also...
Yeah, but they both are very bad. I mean, I claim that they both are very bad. I can claim, make my claim, because there are no functions which belong to this reproducing Hilbert space, because they kill, you would think that all differential functions belong, no, because even constant doesn't belong to
Right,
reproducing
yeah,
Hilbert.
constant is not in this.
Yeah, yeah, because they have their own problems, because the universal, yes, but basically your technology depends on all these functions and reproducible Hilbert, but they don't have decent functions. So there is a problem with both of them, with multi-quadratic and with Gaussian, with this quadratic exponential. But if you
so
take...
you think the multi-quadratic one is too smooth then?
It's too smooth, yes. You cannot take infinitely differentiable kernels, because you need infinitely many derivatives to see anything, in a way. So that's kind of my claim. So because yeah, you need to take something in between, but you don't have many derivatives. Okay, one or two. Okay, maybe two derivatives. Is
So
fine.
which kernel would you use?
I don't know.
What do you know?
Matter. Everybody in the computer experiment they use matter, but
Yeah.
3-2, 5-2.
No, but after it depends, because you Anatoly, you have this point of view, geostatistic and things like that, where you're right. But I think for machine learning, Gaussian is fine.
No, but here everything depends on Hilbert space, on the reproducing Hilbert space, and on these functions. Which
Yeah, but so you don't claim that you just want a function that do the job. You don't want like the...
I mean, this is enough to pull samples from my generator to my...
Yeah, it's exactly that. You want
So,
to do the
yeah.
job. And,
Yeah. I mean, at least here, you know, the performance that we are getting on the tasks, I think it will be interesting to see, like, so this paper here, which I, like, there was a paper called Coulomb-Gann, where is it? I didn't have it on the slide. Anyway, yeah, they were using a different kernel, but I cannot remember if it was, I fear that it was the inverse multi-quadrate kernel, so you will still complain about that one. Yeah, anyway, the one that we used, I think, was inverse multi-quadrate kernel experiments, but that works well enough, as you'll see. Yeah, for this task. Let's see.
I know why it works, because it approximates the least kernel. So you take this parameter very small, and it's almost almost degenerate. I mean, almost unbounded.
Okay.
So that's exactly my question. So about unbounded kernels. So my claim is that unbounded kernels should work better in a way,
Okay.
in somewhere, and that's why multi-quadrate kernel works, because it approximates this unbounded one, the least kernel, which goes to infinity.
Okay. I mean, it is the one we used, so I just,
So maybe what's your regularization parameter?
this I don't remember. Yeah.
Small one or?
Yeah, I would have to check actually how sharp it is. I
Yeah,
have
how
to-
sharp, yes. That's
I,
important, because
yeah.
if it is very sharp, then I'm right. If it is not very sharp,
Okay.
then you're right and I'm wrong.
Yeah. No, I don't know. I can check that.
So my claim is that it works because it approximates least kernel.
Okay.
So it's,
Okay.
because, and then if you start using least kernel, it should be better with no derivatives. Maybe not. I don't know.
Well, no derivatives is a problem because then you can't optimize by. I mean, when you're doing backprop, you need derivatives. So the best you can do is to use a differential approximation. Like if you have a nice kernel which is non-differentiable, you have to approximate it by something that is, because otherwise you can't learn. So that becomes its own problem. Yeah. So I'm gonna I'll skip over the. Like there's some long story about how to evaluate the thing, but I think I'll skip that because we're coming. I guess it's at 6:30. We should stop more or less, right? I can just tell you what we use to evaluate the sample quality, which is we just use an MMD on a pre-trained neural network, like a low-order polynomial MMD on a pre-trained neural network, and this is our evaluation. It's kind of funny because it's a very obvious thing to do. But the main methods that people use for evaluation are like really like troublesome. which is a nice way of saying wrong. So they have like severe bias, which means that the number that they get depends on how many samples they give the machine. And like they can actually change the ordering of which method performs best depending on how many samples they've shown it. So it's like real nonsense. So anyway, like,
Is it the proper kernel? This
Yes.
one.
well, this is just a heuristic. So we're just saying like basically compare the first 3 moments of the output of the pull-3 layer of the inception network, which is a reasonable good feature expector. But it's not. It's not
should be
deterministic.
positive, definitely.
It's positive, definitely.
Good code, it's not for no
Yeah.
It is, no problem.
Yeah,
It
yeah,
is,
it is
and
positive.
characteristic
And
as
it's what you
well.
know
No.
is,
No.
X transpose Y is, X
Yeah.
transpose Y plus 1 is, and
And
after
then
you
you,
multiply
yeah,
it
you
as
take
you
powers
do
and stuff.
Ah, yeah,
so
yeah,
it's a
okay,
legitimate.
okay.
No,
Okay,
yeah,
right,
yeah,
right.
yeah.
But
And
not
it's-
characteristic.
Yeah, but not characteristic. Yeah. This is in TensorFlow. So if you're using TensorFlow,
But
you
it's
can
called
find this.
dimensional.
Okay, so let's see now, like here we are going to compare with actually the papers that appeared in April this year. And like when our NIPS paper came out, we had the best performance. Now Google has made a paper for ICLR next year, which beats us. But that's the circle of life, so that's okay. I'm going to skip to the real pictures. Okay, so here are, like each of these is worth $432,000. These are images that were made using our like latest neural network, trained on celebrity faces. So what you see here is the score that we get. Like this is a quality measure based on simple MMD on data, where we are doing best. We are also doing best using like older metrics with face. That's interesting. So what you can see is that there is reasonable images of faces with a few exceptions. So yeah, like there's some strange ones here and there, and there's like Conchita Wurst over there. If you watch Eurovision, some football player. Yeah, so it's it's not too bad.
can
So-
you recognize somebody now?
No, so these are not like, you can try and do like a birthday paradox thing, like find the exact matches, but these will not give you an exact match. Yeah. So these are just like random celebrities generated. The other thing we did was to train on ImageNet, which is a much harder task than generating celebrities because it has much less clear structure. So ImageNet has 20,000 classes, you've got like a 1.5 million images, and you're trying to train a neural network on ImageNet to generate like objects from the world. So these can be something like a little dog, or it can be like a scene in the country, it can be like scuba diving, like all of these correspond to somehow scenes that you might expect to see in the world. So training on ImageNet without labels is something that people only were able to do this year actually in ICLR. And we're comparing with 2 of the papers that succeeded in doing that. And we have at least slightly better performance than they have on our scores. So visually,
I'm
this
talking
is,
about the whole image.
yeah, all of ImageNet, yeah. So before, like this year, what people would do is they would say, okay, I'm going to train on just the dogs, or just the planes, or just the cars, whatever. If you tried to train on all of ImageNet using the older GANs, it would just get stuck. It would give you like static or noise or junk. So training on all of ImageNet is like a recent thing, yeah. Yeah, but we can, like we trained, it's converging, it's giving quite reasonable images, using the method that I described, which is a special gradient regularized MMD on convolutional features on images. Yeah. So this
So
is,
it's
How long does it take? Couple of months?
no,
Couple of
we could train it even on non-Google equipment. So our I think we had like 3 1080s and we trained it for 2 weeks, and that's so it's reasonable. Like the cost is not expensive to do. Yeah. Like the one that Google beat us with, like that is crazy. Like if you read their paper, they've got like a warehouse and like
GPU for
yeah,
GPU.
yeah, that's really ridiculous. So they beat us by engineering, not by science. So yeah, so these are other categories, but all of them are pretty good. Oops, I wanted to go back. Yeah, so I just want to emphasize that like the software that we use to generate these is all online, so you can like download it and try it, and sell it at Christie's for a lot of money. And yeah, I can, of course, thank all my talented co-authors, and particularly my students in this column. And This is kernel beer, which is a delicious beer you can buy throughout the UK.
Thank you very much. I think it's very, very, very useful talk. What we want your slides.
Yep.
I don't know, we probably, me and Sasha, we don't want any more questions, but maybe somebody else wants to ask something. Because I really think that you can try think about the kernels. You just said that you don't like them. And singular kernels with singularities.
Yeah.
But what we saw, these kernels work much better in somewhere else when we try to generate all these uniform, very uniform random, uniformly distributed points.
I see, like the...
Because you really, they really pay big points if they come close. So, anyway.
I see.
But we don't have reproducing Hilbert spaces because reproducing Hilbert space requires boundaries.
Right.
But most of the things, all these characteristic properties of the kernel, etc., it all works. And MMD works, everything works. So, but I think it was mentioned in that survey, which you mentioned, but it was not proved.
Yeah, but it works, but so even if you are with some data on clinical stuff, you have to make some big approximation.
Maybe that's why this...
and you fall, because you have the one, you take kernel, you can make them arbitrarily large at 0.
Yeah, maybe it's multi-quadratic, maybe it's your multi-quadratic.
Could be, yeah. Because this is at least a good differential.
The one which is, I don't remember English paper, epsilon.
So, is it clear where the difference is coming from in your latest approach? So you had the norm of the gradient, and then you had these two other norms.
Right.
And
Yeah.
you were making everything less than or equal to 1.
Yeah.
And so your constraint on the gradient was automatically false. I mean, I don't know if it was the same norm
This
as
is-
in the previous people who
Yeah,
had that E of that, right? So I don't know where your success is coming from, and
Yeah.
which of those three terms has most impact?
Yeah, this is a very good question. And the answer is actually, it depends on where you are in the optimization. So in the early stage, it's a good idea to make this lambda very small. And so these dominating, when you get towards the end, it's a good idea to make lambda very large. And so we actually adjust lambda as we optimize, yeah. So basically, like, when you're close to the solution, then the features that you get from MMD are very useful. When you're far from the solution, you should just have like some simple like gradient requirement, and that's enough. Yeah.
So another question, what is not clear to me is, so you use this MMD, but you could do things in Wasserstein. Everybody seems to be talking about Wasserstein.
Okay.
Why MMD? Anyway.
I have actually, that's an excellent question. So the initial work, like this was intended to approximate Wasserstein, not this one, sorry, this one, right?
Yeah.
In the sense that you can't make the gradient uniformly bounded on the whole space, so you just make it close to 1 on a restricted part of the space. Now, there was sort of two things that followed on from that. One of which I think is very interesting. So Marco Couturi has done a lot of work on synchron estimating for Wasserstein. Like he's got very sophisticated estimators for Wasserstein distance, and he tried to make them work for GANs. So it didn't work so well. And what we concluded from this is actually the problem of solving, like the problem of training a network to generate images close to a target set of images is not well solved if you have a very, very good estimate of Wasserstein. If you have a really good estimate of Wasserstein and you give that as your signal to your generator, it's not going to make good images. So basically, like, you need to get something worse than Wasserstein if your goal is to make a good, and so this is what led us to think, well, actually, what we want is a witness function that is just smooth over the variation of our data, and that's probably what our generator needs as its target. And indeed, like, that gives very good performance. So like having data adaptive smoothness is much more valuable than having like uniform gradient penalty over your whole domain, which is what Wasserstein gives you. Yeah, but that's an excellent question, because we were puzzled by that for a very long time. Because like Marco had this amazing Wasserstein thing, and it was, it's brilliant and it works really well. You can prove it's close to Wasserstein, but in this task, it's not doing well. And we were very confused by that. Yeah.
One question, I'm dying just to ask you.
Okay.
Everybody, whatever I saw GAN, it was for images, yes? Somebody did for text. Can you generate something with text that you can recognize? Yeah.
So
I never saw any articles.
I do not have a good answer for that, because for that you would need to think about, like, you know, how
Vector
to,
representation, number,
representation,
yeah.
I need something
But you know, there is a
differentiable.
Google this,
Yeah,
billion something, they map all words into this 100 space.
right, yeah, they have this exactly, like, word to vec, or, yeah.
Yeah, okay, yeah, they have this, so
Yeah,
it's enough. So I
Yeah.
want to do the same, just to student to generate
Yeah,
poem or whatever.
yeah,
In 100-dimensional space.
Okay, just normal document, okay, just generate me nice, beautiful article that I can send to Nature. It's a complete crap inside, but they will publish. This is what I want.
But they always published.
Yes, okay, yeah. But I want to look scientific, yes.
Yeah, but
No,
that's,
the question is-
lots of
yeah,
software is doing
one that
that.
works, yeah, for
Yeah,
scientific.
the question is, can you do GAN for text?
so people
I never
have,
seen
yeah, people have done, there have been some work on that, I haven't read it though, so I can't comment.
Yeah,
I know that when
I don't
people
know
are
about-
generating sequences, they use something like LSTM.
Yeah.
So, you know, here you want to basically have, like, you know, you have a random process, it has dependence, the dependence should
No,
be
but the main question then is how to separate. What
Yeah.
is the cost? Because generate, yes, translation, from one to another, yeah, we can generate.
Yeah,
Let's yeah, but how we can, how it called this?
yeah, like make like an adaptive, a critic, a good teacher, and this I don't
Money,
know.
yes.
This I don't know, yeah, I haven't read the paper.
No,
But
I
there
haven't
is,
seen
there
it.
is, yeah,
Maybe
yeah.
you know.
Yeah, no, so there are papers on this, if you look at like text generating
Oh.
GAN, like you'll find some references, but I haven't read them, so I don't know really what they're doing. Yeah, I'm suspicious of them, but I haven't seen it, yeah.
All right, any more? All right, thanks very much.